Hi guys, today I want to talk about digital electronics and about digital logic and particularly logic gates. So these are common types of circuits, or if you like, building blocks of larger circuits, and we come across these a lot in electronics repair. Logic gates may be part of integrated circuits, or they may be implemented just using transistors or MOSFETs. And you need to understand logic to be able to repair these sort of circuits. There's quite a bit of, not exactly mathematics, but algebra involved with digital logic and logic gates. But from the point of view of repair, you don't really need to know that. You need to understand circuits and how to measure voltages and how to work out from those what is happening with the circuit, what it's supposed to be doing, and how it's behaving if it's faulty or if it's working. Okay, so let's start from the best place to start. Let's start from the beginning. Yeah. Electronics then, digital electronics. What does digital mean? Well, electronic circuits work basically by directing current in certain directions at certain times. I think that's a fair way to put it. By applying voltage, you can direct current to flow where you want it to flow, and just by that simple principle, you can do anything that you can do with electronics. And electronic circuits basically fall into two types or two classes of circuit. We have linear and we have digital. So we have linear electronics, we have digital electronics. What's the difference? Well, in a linear circuit, the voltage, which effectively is driving the current flow, can vary at any point in the circuit, basically from 0 to whatever voltage the maximum supply voltage is. So, for example, if we're amplifying an audio signal in a linear amplifier, we can have a very simple little circuit like this. Transistor amplifier, a speaker, good off the page, ground, some resistors because we need them, and we can feed into here a linear signal. So this is basically a waveform which varies in voltage over time, and coming out of it, or what should I say, driving our speaker, we have an amplified version of that waveform, so it's bigger. That's a typical linear circuit. But the basis of linear electronics is that the voltage can vary and can be any voltage between effectively 0 and the maximum voltage that's available in the circuit. Okay, positive or negative. So that is linear electronics. Now, in actual fact, all electronic components are linear. I'll say that again because this is very succinct and very true. All electronic components are linear devices. Okay, whether it's a resistor, a capacitor, an inductor, whether it's a diode, a transistor, a MOSFET, or anything else made up of those building blocks, they are linear devices. But they can be configured to work in a way which is basically digital. So what's digital? Well, the word digit can mean a finger, fingers, digits. But it can also mean a number, a numerical, a digit, the digit 1, 2, 3, 4, 5, and so on, or digits, okay? And digital circuits can also handle mathematics, digits. Basically, a digital circuit is something like this. It looks like this, really. Resistor in, transistor, resistor supply, okay, put another resistor here, why not, in, out. Now that is the same as this. It's a linear circuit, but it can be used in such a way that the voltage applied to the input is such that either this is fully turned off or it's fully turned on. So by selecting and using the correct voltage to drive the circuit, we can create effectively a digital circuit, in as much as the output can either be on or off. It can either be whatever the supply voltage is, say 5 volts, or it can be 0. And it will never be anything in between, because the voltage we're using to drive the circuit makes it behave in that fashion. So this is how we can effectively make a digital circuit, one that has 2 states, on or off, 0 or 1, out of an analog device. Because electronics used in this way only have 2 states, on or off, the way they handle mathematics is called binary. Binary. There are only 2 possible states on the output of this, 5 volts or 0 volts, never anything else. So binary has therefore 2 digits, 0 and 1. Whereas we use a decimal system, 0 to 9 or 1 to 10 if you want to think of it that way, but 0 to 9 is more correct. Where the Romans effectively had, with Roman numerals, a 5 base system, if you think about it. So you had, I'll draw it, you had I, V, 1 to 5, and then you start again, VI, VII, and so on, yeah? So that's a base 5. We have a system from 0 to 9, which is base 10. In binary, it is base 2. There's only 2 digits, 0 and 1. There is no more. So what's the highest number we can count to in binary? Is it 1? Well, I'll ask you the other question. What's the highest number we can count to in decimal? Is it 9? No, it isn't 9, because in decimal, when we get to 9, we then map over to 1 0 and 1 1. And what we're really doing, this column, these are your single digits, your units, 1 2 3 4, and this column represent the tens of units times 10. And when we get to 99, what happens next? We go to 1 0 0, and this is the number of hundreds. And by doing this, in actual fact, the highest number we can count to in decimal is actually infinite. There is no highest number. We can go from 0 to as large as you want. You can always go 1 more, and you can go negative, always go 1 more. Binary works in the same way, but we only have 2 digits. So 0 is 0, 1 is 1, and these are your units, yeah? And when we get to 1, the next thing we need to count is 2. So the way we do that, we have 1 0. So the unit is now 1. In this column, instead of being tens, it's 2s. Yeah, it's how many 2s there are in the number, yeah? After that, we can go to 1 1. 2 plus 1 is 3. And we want to go to 4, we have to add another column. So this is your units. This is your 1s. No, sorry, your 2s. How many 2s, yeah? And this is your 4s. And the next column will be how many 8s and how many 16s and so on. So that's binary. So if you think about this a little bit, if we have loads of these transistor circuits, we'll just draw 3 of them. Okay. And we turn each one on or off at different times, we can actually represent a binary number. I'll show you how we do it. So let's have, as I mentioned, let's have 3 of these circuits. Okay. Another one, put a resistor here, output ground, and we'll have a third one. Okay, ground resistor up to here. This is your supply voltage, and this is your output. And we have 3 transistors. Now, although these transistors are linear devices, we know all electronic components are linear devices, we can make them behave in a digital fashion. And by digital, I mean we can make them behave in such a way that the transistor is either fully on or it is fully off, and it's never anything in between. It's either on or it's off. Okay, the way a transistor works, and I made a whole video about transistors, I will link it from this one, but we have 3 terminals: base, collector, emitter, and it acts like a switch. So if you put a voltage on the base, the transistor will turn on, and as the transistor turns on, it will start to draw current through the load, this resistor, and the voltage at this point will drop. So if you slowly, gradually increase the voltage here will go from whatever the supply voltage is to 0 in a linear fashion. Yeah, as you alter the voltage down, it will go up. As you go up, it will go down. So the voltage on here will vary as you vary that voltage, and notice it varies in the opposite direction. The more positive you make this, the more negative this becomes. That's basic transistor operation. But we want to make this work in a digital fashion. So the way we can do that, basically, is either to have 0 volts on here, or have, for example, 5 volts on here. The 5 volts will flow through this resistor, which limits the current into the base. Otherwise, you'll actually just burn the transistor out. But by putting 5 volts on here, enough voltage appears on the base to turn the transistor fully on. So what we can do now is make this work in a digital manner. We can either turn the transistor on or off. If we turn the transistor on, the voltage here becomes 0, basically. And if we turn the transistor off, it becomes 5 volts. Because 5 volts we're going to use as our supply voltage. It doesn't have to be 5 volts. It could be something else. It could be 3.3 volts, 1.8 volts, or whatever other voltage you think we should be using to switch our circuit. Now let's make this count up in binary. Okay, so this transistor, we'll call this the units. This is how many units we have. Yeah, and in units we only have 2 possible units. We have 0 or 1. Okay, now we could in theory decide that 5 volts equals 0 and 0 volts equals 1, but it's probably easier the way the human mind works, or certainly the way mine works when it's working properly, is that 0 volts is 0 and 5 volts we can call that 1. Yeah, because we only have 2 digits. We don't have a 5, so we've got to call it something. We'll call it 1. So this can be our units, and the voltage on here, depending on what we put on here, can either be 0 volts or 5 volts. This can be our 2s, how many 2s there are in the number, and the same applies. Yeah, the output can either be 0 volts or 5 volts, 0 or 1. Yeah, and this is how many 4s we have, how many number 4s, and again, the output, when this is on, this is 0, when this is off, this is 5 volts, and that is what we're going to call 1. So let's count up some numbers with our circuit. Yeah, let's do it. We have 3 lots of numbers. We have 1s, we have 2s, and we have 4s. Or units, 2s and 4s if you like. Right. Well, we'll start off with all the transistors turned on. They're all on, okay? By which I mean there is 5 volts coming into the resistor on each one, yeah? They're all on. So all the collectors will be 0 volts, okay? So this column, this is the voltages we see effectively on the collectors, yeah? We see 0 on this one, 0 on this one, and 0 on this one. all on. Let's say we turn this one off. This now goes to 5 volts. Well, we're going to represent 5 volts with a 1 in binary, okay? So this one, the 1s, now goes to 1. These two are still turned on, so these are both 0. We've got no 4s, we've got no 2s, but we've got a 1. So that, in decimal, equals 1. In this case, we've got none of any of them, and decimal equals 0. Let's switch this transistor back on and switch this one off. The one that's switched off, the collector will go to 5 volts, okay? Which really represents, as we said, with a 1. So, this one is now on, this one is now off, this one is now on. We've got no 4s, we've got a 2, and we've got no 1s, so that is 2. Let's turn this one off as well. So now this is 5 volts, this is 5 volts, and that's 0. So we've still got no 4s, we've still got a 2, and we've also got a 1 as well, and 2 plus 1 in decimal is 3. This, by the way, is not 11, it's 1, 1 in binary. You don't call it, like 1, 1, 1 isn't 111, it's 1, 1, 1. That's how you work it in binary. Let's carry on, let's just carry on, So what can we do now? Well, we can turn this one off, and we can turn these two back on again, okay? So this one's off, that's now 5 volts, which is a 1, and these two are zeros. 4. Then we can turn this one back off. 1, 0, 1. 4 plus 1 is 5. Then we can do it with this one and put this one here back off again. Sorry, put this one here back on again, sorry. So this one's off, this one's off. 5 volts, 5 volts. This is 0 volts. 4 plus 2 is 6. And then the last thing we can do is switch them all off. So we get 5 volts, 5 volts, 5 volts is 7. And that's how we can count using digital electronics. Okay? So there are basically 3 things, if you like, to come from this. Just to recap, and then we'll go to the next section. We have 2 sorts of electronics. We have linear and digital. They all use linear devices, but they're configured to work in different ways. In a linear circuit, you'll have a varying voltage here, which can be at any value, and you can have a varying voltage here at any value. Okay? Second one, linear components can be configured to work in a digital manner. Yeah? Which is what this is doing. And the third one, that digital circuits can count. Okay? That is the basic principles of digital electronics. This circuit then can count up to 7. Okay, from 0 to 7. It actually has 8 possible states, because there are 8 conditions. 1, 2, 3, 4, 5, 6, 7, 8. And we use one of them to represent 0. If we add more transistors, we can count to higher numbers. So adding another transistor will give us 8s. How many 8s in the number? Another will give us how many 16s. Another one how many 32s. Another one how many 64s. Another one how many 128s. And we've now actually got 8 transistors in our circuit, and that is what we call 1 byte of information, 8 bits. And we can count up to 256. No, I tell a lie. We can count up to 255 because one of the conditions is 0. That's effectively 8-bit processor. That's how they work. That's how they represent numbers. Now we've had a look at that, and you've realised that by adding more columns, we can effectively count up to however many bits we want. We can have numbers however high we want. It's infinite if we have an infinite number of transistors. Let's have a look at logic. So let's see how this applies to logic circuits. Digital logic circuits are closely related to binary arithmetic, which is why we started from the very beginning. So a logic circuit, what is it? Well, it's a circuit that has a number of inputs that can be connected to various devices and the number of outputs that can control various devices. That's what a logic circuit is. But all logic circuits are made up of basic building blocks, and those building blocks are called logic gates. And by using logic gates in various combinations, we can do a whole variety of things. Really, the possibilities are endless, as they say. Logic gates then, which are the building blocks of logic circuits, are a bit like Lego. They're little circuits that do set things, okay? And they actually fall into 8 different types of logic gate. I'm going to cover 9 types, and the reason I'm going to cover 9 types, the 9th one is not actually a type of logic gate, but is a circuit that's used so often in conjunction with logic gates, I really need to include it from the point of view of electronic repair, which is what this is about, okay? Logic gates basically were invented by a guy named Boole, okay? And they use a type of mathematics called Boolean algebra that defines the operation of the gate. But this is something designers need to know. It's not something repairers really need to know. So I'm not going to cover Boolean algebra. There's plenty of tutorials out there if you want to learn it. But in my opinion, unless you're interested, it's not something you need to know to be able to fix stuff. So what is a logic gate then? Well, it's a circuit that has certain characteristics. The first thing is it will only ever have one output. All logic gates have one output, but they will have various numbers of inputs. It could have one input, 2 inputs as common, 3, 4, 8 inputs. It could have a whole different number of inputs, and the number of inputs will depend on how many signals effectively you want to monitor, how many devices you want to monitor to produce the output. The output will only be in 2 conditions, like we were just describing with binary arithmetic. It'll be 1 or it'll be 0. It'll be a voltage present or no voltage present. Those are the only possible output states, and they're represented in different ways. It doesn't really matter which one you use. But if you're looking at component data sheets, you will see various different terminologies. So you should need to know what they are and then use whichever one you're the most comfortable with. I use 2 basically different types. So the output we know can either be on or it can be off. This is not actually quite true, by the way. I'll talk about it later before anybody gets into the comments below. Yes, Richard does know, but for now we can consider it to be on and off. The principle is the same. The output is on or off, okay? We know from what we were just looking at that on can be represented by a 1 and off can be represented by a 0. It could be represented the other way round, but it's the logical, yeah. It's the logical way to do it. So the output can be on or off. It can be 1 or 0. We know 1 is when a voltage is present, so that can be classed as high, a high signal, yeah. And we know that 0 or off is when there's no voltage present or low, yeah. So another way to represent the output is H or L, high or low. There's another method as well, and this is to do with Boolean algebra, which I'm not going to be covering, but a 1 can be considered to be true, okay, so the output could be classed as T, and a low or a 0 could be considered to be false or F. So those are really the 4 ways you will see the output represented. Another way you will see it, and I'll mention this as well, as you might see a low represented in these ways, but this is not in logic tables, but this is in circuits, so you do need to know them, yeah. The output, whether it's a 1 or a high, I'm going to use this during this tutorial, high and low, H and L. The other one I commonly use is 1 and 0, and I tend to kind of intermingle them, you know, as I feel like it, depending on if there's an R in the month and what day of the week it is, yeah. But I'm going to use this in this tutorial. When we look at schematics, the output from a logic gate will probably be given a name. It won't be classed as H or L. It'll be classed as something like enable or power good. Yeah, it'll have a name that means something. 3V on. The signals will be given names, which helps you to understand the schematic. If that symbol has a line over the top, it means it's low. It's effectively a logic 0. Yeah. So in this case, a 0 volts means the power is good. Yeah. In this case, a 5 volts means it's enabled. We can also put enable here. In this case, with a line above it, enabled is low. So if that connection, that pin on that transistor or chip has 0 volts, it's sending a power good or an enable. In this example, it's sending, if it's a high, 5 volts. So that's kind of used to represent a 0. Sometimes it's like this with a hash in front, hash PG. Sometimes with an asterisk in front. Yeah. Occasionally even with a minus in front. All those are things you will see in schematics that effectively represent a logic 0 or a low. Okay. For the point of view of discussing logic gates, I'm going to use these two, high and low. High being whatever the supply voltage of the circuit is. As I mentioned, common ones 5 volts, 3.3 volts, 1.8 volts, 1.05 volts in things like motherboard circuits with PCH chips and things like that, and then 1.05 volts in GPUs could be lower. Yeah. PCI Express, I think, is about 0.9 of a volt. But the voltage doesn't matter. It's just a high or a low from the point of view of the way the circuit works. Okay, now we understand that. Let's have a look at the 8 logic gates plus the 1 I'm going to add for good measure, and you'll see why. The most basic logic gate then is a buffer. The symbol for it is this. A bit like a diode without a bar in it. That's the symbol. Buff is what it's called. Buffer. And this gate, and all gates, all logic gates, are represented using a truth table. This is kind of where this true and false comes from. Yeah? A truth table shows the condition, all the possible conditions of the input or inputs, and the output you will get for that condition. So let me show you the first truth table, okay? This circuit has one input. We'll call it A, for reasons we'll see in a minute. It has one output, and we'll call it out. This is quite commonly sometimes called Y, for reasons not best known to myself, okay? What are the possible conditions? Well, the input can either have 0 volts or whatever the supply voltage is. Let's use 5 volts for this discussion. Just makes it easier, yeah? The input can be 0 or 5, okay? 0 is a logic 0. Let's do it the way I'm going to do it. We'll call it low, yeah? And 5 volts is high, okay? Use whichever one you prefer to use. If the input is low, on a buffer, the output will be low. If the input is high, the output will be high. That's what a buffer does. And this is called a truth table. Okay. Now the first thing you're going to ask, Richard, what's the point of a buffer? Because whatever's on the input is also on the output. Can't we just call that a piece of wire? Yeah, we can call it a piece of wire. Because that's what it's doing. It's really doing what a piece of wire does, but with an exception, a big exception. A buffer is usually used to drive a circuit that requires more current than the source can actually provide. So if this is a CPU, and this is, for example, an LED, the CPU, being a low power device, can't drive the LED directly, so it uses a buffer. He puts a high on here, which puts a high on here, which turns the LED on. And he puts a low on here, which puts a low on here, which turns the LED off. So that is the most simple logic gate, and it's called a buffer. Okay, let's look at the next one. This also has one input and one output. Only these two gates have one input and one output. And this is called a NOT gate. It's a NOT. Not a knot with a K like what you get tangled in a piece of rope. A NOT like as in no, not never. Yeah. A NOT gate has a circle on it. And the circle basically represents an inverter. So whatever would normally come out of the gate is inverted. Yeah. So in this case, if you put a low in, you get a low out. With a NOT gate, you put a low in. Instead of getting a low out, it inverts it. You get a high. Okay? And the opposite. Truth table. Input A. Output, I'll stick with out. Input, it can either be low or high. There's either no volts on here or there's 5 volts on here. Nothing in between, yeah? Low or high. If the input is low, it inverts it, the output is high. If the input is high, it inverts it, the output is low. That is a NOT gate. Easy way to remember it, the output is not the same as the input. The output, whatever is on the output is not what is on the input. NOT gate. Okay? Let's look at some more gates. The next one we have then is an OR gate. So with an OR gate, we have 2 or more inputs. All the rest of the gates, all of them now will have 2 or more inputs, but they will only ever have one output. The symbol for an OR gate is this one. Okay? And this is the out. And we've now got 2 inputs. OR. Why is it called OR? Because the output is high if either of the inputs are high. If that is high or this is high, this will be high. Let me do it again. If this is high or this is high, this will be high. Okay? Truth table. We now have 2 inputs, A, B, and we have an output. Shall we call it Y? Because it's commonly done that way. We could call it out. A, B, Y. Okay? How many possibilities are of the input? Well, there's not 2 possibilities. There's actually 4. A can be low, 0 volts. B can be low, 0 volts. Yeah. A can be high, and B can still be 0 volts, low. Yeah. B can be high, 5 volts. A can be low, 0 volts. Or they can both be high. They can have 5 volts on both of them. That's the only possible combinations. It's only possible combinations with 2 inputs. What's on Y? The out. What's on Y? Well, it's an OR gate. I said when this is high or this is high, the output will be high. In this case, second one down, A is high. Yeah, so the output will be high. On this one, B is high, so the output will also be high. On this one, is this high or is this high? No. The output will be low. Okay? We've already done it. Is this high or this high? Yes, this is high, output high. Is this high or this high? Yes, this is high, output will be high. What about this one? What do you think, guys? What do you think will happen if they're both high? Well, in an OR gate, is this high? Yes. Or is this high? Yes. They're both true. They're both high. Yeah. So the output is high. That is an OR gate. Okay. We have another one. We've had OR. What about AND? AND, yeah, an AND gate. So this is an AND gate. We'll use 2 inputs. I'll show you the bit what happens with more inputs, but should be fairly obvious. An AND gate is drawn like this. Input A, input B. It's an AND gate. You can probably figure out where this is going, guys. Can you figure out where this is going? Yeah, you're going to figure it out. So, with an AND gate, if this is high, 5 volts, and this is high, 5 volts, the output will be high. Otherwise, it will be low. Truth table. A, B, Y. Again, there's only 4 possible combinations of inputs. They both have 0 volts on, low, low. A has 5 volts on high, B is 0, low. B has 5 volts on high, A is 0, low, or they both have 5 volts on. Let's work out the truth table. It will only give an output if A and B are high, so you can see it, can't you? Are A and B high? No, they're not. Output is low. Are A and B high? No, only A is high. Output is low. Are A and B high? No, only B is high. Output is low. Are A and B high? Yes, they're both high. Output is high. 5 volts comes out. 2 lots of 5 volts in, 1 5 volts out. That's an AND gate. Okay. There's one more basic type of gate, and then we'll work on the variations. So this is called an exclusive OR gate, and the symbol, because I've messed it up, is like that. Okay, it's like that. Okay, made a mess of it. It's still like that. Yeah, look. Okay, that's how the symbol is. Right, 2 inputs again, A and B. 1 output, Y. Truth table, A, B, Y. 4 possible combinations, we already know what they are. Both low, this one high, this one low, this one low, this one high, both high. What do we get? XOR, exclusive OR, XOR. If A is high or B is high, the output will be high. So, like an OR gate to some extent. Is A high? No. Is B high? No. Output must be low. Is A high? Yes. B is low. Are A or B high? Yes, this one's high. Output is high. A is low. B is high. Is this or this high? Yes, this one's high. Output is high. What about this condition? Well, this is the difference between an exclusive OR and an OR gate. The reason it's exclusive is because you only get a high if this or this is high, not if they're both high. That's why it's called an exclusive OR. So that is your 5th basic type of gate. 5. Just number them so we knew what they were. We have the buffer 1, we have the NOT gate 2, we have the OR gate 3, we have the AND gate 4. Okay. These ones are kind of combinational ones now, but they are used so often they are gates in their own right. So this one is a OR gate. Okay. A, B, Y, and we put an inverter on it, like we made the buffer into a NOT gate. This makes an OR gate into a NOR gate. Not OR, NOR, not OR. And it works the same way as an OR gate, but the output is inverted because that's what the little circle does. Truth table, A, B, Y. We know there's only 4 combinations on all of them. That's the only possible combinations. Let's look at it like an OR gate, which we've just understood, with an inverter. Is A or B high? No, they're both low. So the output should be low, but the inverter inverts it, the output is high. Okay? Is A or B high? Yes, A is high. So the output should be high, but the inverter inverts it, low. Is A or B high? Yes, B is high, so the output should be high, but the inverter inverts it, low. And in the case of an OR gate, if they're both high, the output should be high, but the inverter inverts it, it's low. That's a truth table for a NOR gate. And you can see where this is going, can't you? We can put an inverter on our AND gate as well. Okay? A, B, Y. We know the truth table for that one. Let's draw it again. A, B, Y. We're going to put a 0. Told you I tend to synonymously use them both. Yeah, low, low, high, low, low, high, high, high. If you prefer zeros and ones, by the way, use them. Yeah, doesn't matter. Use what you prefer. Okay. Are A and B high? No. Output should be low. The inverter inverts it high. Are A and B high? No. Only A is high. Output should be low. Inverter inverts it high. Same with this. High. Are A and B high? Yes. The output therefore should be high. The output should be high. The inverter inverts it low. Okay. That is 6, 7. Do you know what this one's called? It's a not and. NAND. You've probably seen this. Yeah. It's the way kind of a flash memory works. Yeah, because it contains lots of gates basically. Okay, NAND. Unless somebody's going to tell me that's not why it's called NAND memory. I'm sure that's exactly why it is called NAND memory. Okay, so the last one, well, we've only got the XOR, and we can put an inverter on it. Yeah, we can put an inverter on it. Not only can we put an inverter on it, we can also draw it properly this time. Yeah, and we can actually draw it properly. We have another opportunity. Yeah, to draw it right. Okay, we've redeemed ourselves now. This one, A, B, Y, truth table. A, B, Y, low, 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 high, high. Well, I've even drawn it. I'll keep it going the same as your ones. Low, low, high, low, low, high, high, high. Let's not make this any more confusing than it was already. Now let's put an inverter on it. What do we get? Well, like the XOR, when both the inputs are low, the output should be low, but the inverter inverts it, it's high. Yeah. When A is high, B is low, output should be high, inverter inverts it, it's low. Same with this one, when B is high and A is low, output should be high, inverter inverts it, it's low. And when both of them are high, because it's an exclusive OR, the output is low, and the inverter inverts it, so the output is high. That is an X NOR gate. And those basically are your 8 types of logic circuits. But I'm going to include the 9th one, just because you always get one better on this channel, yeah? We always go one better on this channel. Right, what have we got? It's not a logic gate, but it's used so often in conjunction with logic gates, I will show you. And this is a kind of operational amplifier circuit. I'll do a whole tutorial on op amps or operational amplifiers, but it's used in a certain way. And what it does is it compares the voltage on this input with this input. So this is analog. The voltages can be anything. This is the plus input. Sorry, this is the non-inverting input. This is the inverting input. Okay, and it effectively, although these are analog, what it does is it compares the two and gives basically a digital output. So if the voltage on here, we'll call them A and B again, let's call this Y again, yeah. If A is higher than B, it will give a 1, and if B is higher than A, it will give a 0, high and low. So we can have a kind of truth table, but it's not really a truth table. So we have A, B, Y, yeah. So if A is higher than B, the output will be high. Okay? If B is greater than A, the output will be low. What will happen if the A and B are exactly the same? Well, the answer is actually the output is indeterminate. It's an indeterminate state, basically. But normally, because the internal circuitry, it will go one way or the other. Yeah, high or low. But the way the device is used, it's used in such a way that A and B will not be the same. Okay, the way the circuit is designed, that condition doesn't occur. So this is a comparator. It's not a logic gate. I won't put not, because that's the name of a logic gate. It isn't a logic gate, but it's used so often in circuits in conjunction with logic gates, it needs to be included in this tutorial, because we want to learn how to fix stuff, yeah? I would just like to show you a couple other things about logic gates, and then we can go on to some practical. We can make some circuits using transistors and MOSFETs, and we can see how they work, and we'll learn a few more things, and this will lead into the repair side of it. But I did mention previously that a gate, a logic gate, can have one or more inputs. Only buffer and not have one input, all the rest have more than one input. So for example, you can have an AND gate which has 4 inputs, A, B, C, D, and any other number of inputs that you want, to be quite honest. Okay, and it still has a truth table in the same way, but now we have 4 inputs, A, B, C, D, and 1 output, Y. There's always 1 output. Because we've now got 4 inputs, there's more possible combinations of inputs, and in fact there are 16 of them, and I'll show you quickly how to do that actually. So I was going to put zeros, but I'll put lows, okay, because we're using low. So all inputs can be low, okay. These 3 can be low and this can be high. Low, low, high, low. We can have low, low, high, high. Then we can have low, high, low, low, and so on, yeah. And if you look, what's happening is, you'll see that basically this one, which is the digits, are alternating between low, high, and it'll keep on doing that, yeah. It'll do it for all 16 combinations. So we've got 5 here, yeah. So we can have 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 combinations, and it just alternates low, high, and this is doing the same thing, but it's doing it at a slower rate, half the speed. So this is going low, low, high, low, low, high, and so on. So low, low, high, low, low, high, low, low, high, and this is just one of these things about digital electronics, binary, yeah. The next one, although I didn't draw many of them, I can tell you now it's doing 4 lows, 4 high, 4 low, and 4 high, and so on. So we can go high, 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 high-de high, yeah, low, 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 high, 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 high. And the last one, you guessed it, yeah, it does 8 times over again. 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4, 5, 6, 7, 8. And it will continue to do that. The next column, if there was 5 inputs, would be 16 times low, 16 times high, and so on and so on and so on. Yeah. So it's easy to draw them like that. Because this is an AND gate, the only condition that will give you a high on the output is if all 4 inputs are high. So that is high, and all the rest are low. Every single one of the other possibilities are low. Okay? What if we wanted a 5 input AND gate? I mean, you can get 1, 2, 3, 4. I think the next one you can get is probably 8 inputs in an integrated circuit. So you wanted a 5 input AND gate. Well, you can actually do that by taking an 8 input AND gate. 1, 2, 3, 4, 5, 6, 7, 8. This is where I now found dodge root too big. Okay. And what you can do is, if you only want to use 5 inputs, A, B, C, D and E, the other inputs, you can connect them all via a resistor to 5 volts. So these will always be high now. Yeah, they effectively ignored, they're always going to be high, never anything else. They're connected via a resistor. So now you can put your 5 inputs on here. Yeah, you've made an 8 input AND gate effectively into a 5 input. What if you wanted a 5 input AND gate, but you only wanted the output to be high if A, B, C and D were high but E was low? Well, to do that, quite simple. You connect an inverter on E. So that will now invert E. So you're making your own logic now. There's no particular name for this. It's the gate which only gives a high output if the inputs are, and I've drawn an extra one, so we need to put it in, high, 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 low equals a high. And in fact, you might have a case where you wanted output to go high if A, B and C are high, but D and E are both low. Or, because I haven't got the space to draw it, maybe you wanted to do it where A and B are high, C is low, D is high, and E is low. So you can connect another inverter chip here. Yeah, and this will now give you a high output only if this is high, high, low, high, low. Only that combination of inputs will give you a high. So you see, you can make your own logic out of a combination of logic gates. And this brings us to something really quite interesting. The only logic gate you ever actually really need is a NAND gate. And the reason being, because you can make every single logic gate from NAND gates. Yeah, every single possible logic gate can be made from using several NAND gates. So let me just show you. What if you wanted to make an inverter? Well, you can actually make an inverter, you know the truth table, inverter, input is high, output is low, input is low, output is high. You can make that out of a single NAND gate. All you do is, you take your NAND gate and you connect both inputs together. You've now got one input and one output. If the input is high, the output will be low, and vice versa. You've now got here an inverter. Well, if you wanted to make a buffer, well, you can do that as well. Because all you need to do now is you take 2 of these inputs connecting together to another one with the inputs connecting together and an output. Again, you've got one input, A, and one output, Y. If this is high, then both the inputs of this NAND gate are high, which gives you high for AND, inverted gives you low. So both these inputs are low, which gives you low, and then AND inverted for the NAND gives you high. What about this? Let's have a look at this. Say we take a NAND gate. Okay? a 2 input NAND gate. And what we do is we connect an inverter to 2 more NAND gates, and then these 2 NAND gates, we connect the 2 inputs together. Okay, so we've got 3 NAND gates now. These 2 are wired like inverters, both inputs together. They're an inverter, yeah. So we've got the truth table. We can draw inputs A, B, and Y, and we can work out what this does. A, B, Y. What's the circuit do? Well, if A is low, let's start with them all being low. So we've got low and low, we've got high and low, we've got low and high, and we've got them both being high. That's possible combinations, yeah? What happens if they're both low? Well, if A is low, internally this AND gate has 2 low inputs, gives a low output, inverted because it's a NAND by the inverter, so the output of this will be high. Okay? And the same with B. A low input will give a low internally if it was an AND gate, inverted to high. So coming into this gate, we've now got 2 highs. Internally, if it's an AND gate, you will get a high, but there's an inverter on the output, so it gives you a low. So 2 inputs low give you a low out. Let's look at the other ones. So in this case, we've now connected A to 5 volts. So both inputs to this now, because they're connected together, are both high. If this was an AND gate, internally you would get a high. Yeah, A and B are high. It's an inverter on it. It's a NAND, so we now get a low. But this one is still doing what it was doing before, yeah, low and high. Yeah, this is still doing what it was doing before. We still have a low on B. So low and high going into our AND would give a low, which is inverted by the inverter on the output, which gives a high. So that combination gives you high. And the other possibility where A is low and B is high is exactly the same. It's just the low here is now a high, and the high here is now a low. But you've still got a 1 low and 1 high coming to an AND gate, gives you a low, inverted gives you a high. So that's high. What happens if they're both high? 2 highs coming in here, it's an AND gate, so internally we give you a high, yeah, which inverted gives you a low. Okay, this is the same. We've now got them both high, so 2 highs coming into an AND internally gives you a high, which is inverted by the output, which gives you a low. So coming into this gate now, we've got low and low, generates low internally, inverted gives you a high. So that is high. And that is the truth table for that combination of 3 NAND gates. It's also the truth table of an OR gate. A, B, Y. If they're both low, output low. Is A high or B high? Yes, output's high. Is A high or B high? Yes, the output is high. If they're both high, the output is high. So that combination of 3 NAND gates is an OR gate. And you can do that with all of them. There's a rough rule of thumb. I'll just tell you what it is. If you want to turn that into that, yeah, put 2 inverters on the input and change the symbol from AND to OR and vice versa. That is basically how it works, yeah. That is how it works. So wherever there's an inverter, there isn't, and wherever there isn't an inverter, there is. It's you just change it, yeah. That's the rule of thumb, yeah. But unless you're designing circuits, you really don't need to know about it. It's just something I thought that was really quite interesting. That, guys, is the end of part 1. So now you have all the theory you need to understand, to know all you need to know about logic gates to fix stuff. But of course that is only half of the story. So in the second part we are going to build some logic circuits using just transistors and MOSFETs. We can measure the voltages in those circuits, and we can also introduce faults into the circuits and see what happens under certain circumstances. We can also build a few little gadgets like this one. So this is made with 2 comparators and 5 transistors, effectively wired as a logic circuit, and this one basically lights the LEDs in sequence depending on the voltage of the input. I'm going to set the voltage by just adjusting this potentiometer, and you can see they're all off until a certain point I get the green LED, more voltage I get the yellow LED, and then a little bit more and I get the red LED. So we can have a look how this sort of circuit works. Again, we can play around with it, introduce problems, and then see how we can diagnose them. We'll also take a look at some real circuits that you will find in use, for example on graphics cards, on laptop motherboards, where you have lots of transistors wired up to make the power rails come on in a certain sequence, or certain conditions applied before the laptop will switch on. So we can have a look at a couple of real schematics, see if we can work out how they operate and how we would go about fault finding them. So all that's to come in part 2. I hope you're looking forward to that. I hope you enjoyed part 1, and now you have all the grounding you need to understand the next part, the real part, all you need to know about logic gates to fix stuff. Okay guys, I'll see you all soon. Ciao for now.